All right, good morning, everybody. Thanks for being here for the second day of the FDF. We'll start with Alvaro Navarro, that he's from the CMAT Research Institute in Spain. He's a holder of a PhD from Telecom Engineering from the Technical University of Madrid. And he will talk to us about software-generated smart constraints to facilitate FPGA designs. So yes, thanks, Alvaro.
Thank you. So, do you hear me? Yeah, it's high enough, right? So, so today it was digital solutions session. So I thought of two everyday problems, and so I thought, well, the main topic is timing and placement. But I also added in here a couple more things that I will talk to at the end. First, a little presentation. I'm part of TMAT. TMAT has been working in CMS experiments since its construction. It contributed to the construction of the drift tubes subdetector, all the electronics, the readout, and all those things. I have been working here just for 15 years, so I didn't participate in the construction, but I've been working on the two upgrades that have followed. And we've been doing everything electronics related. So between those things, a lot of FPGA stuff, and I'm writing here what kind of platform we have worked with. Mainly my exciting same AMD FPGAs, but also recently PolarFire. So I'm going to talk mainly about what I would call my struggle with timing and how I got to solve it. And finally, I will give a couple of slides about the two completely unrelated topics, but I thought it might save someone 5 minutes of time. So I will just leave this here for a reference. This is the problem we're trying to solve. The muons go through the drift tube subdetector, and they leave traces in the different chambers. And we need to take all those hits together and build trigger primitives. It's somewhat of a complicated problem because the drift time is a lot bigger than the bunch crossing time, the time it takes for new collision to come. So hits can get mixed up, and you have to decide which hit corresponds to which collision. So why did I want to go fast? I'm trying to develop my algorithm for 480 megahertz, so almost 500. Why did I wanted to go that fast? Basically, the answer is throughput. Our algorithm suffers from combinatorial explosion. You have this overlap between different collisions. And so when the detector starts to get noisy or get a lot of signal, you have to try lots of different combinations of hits, and that grows very quick. So we need to do many operations in a fixed latency in order to sort things apart. So this is basically our need, the need for throughput. So due to the system constraints, it's an LHC experiment, so we usually work with multiples of 40 megahertz, and the hardware and the firmware framework that we're using, the most natural frequencies were those 3 multiples of the LHC clock. So I thought, okay, I'll go for 480. It sounds challenging, but it sounds achievable. And I was probably underestimating the challenging side of the equation. So my target for this talk was this number, which is slightly over 2 nanoseconds of timing. So my bottom-up approach in the beginning, which was a little naive, now looking a posteriori, is, okay, I will design, my design can be written in the order of 50 different entities, which are then replicated several times, each one of them. So if I just build each one of those entities in a way that I know it's more than enough, it has a big margin, so I give it a margin of even 350 picoseconds, which it's really a lot in this scale. So I will just then put them all together, and everything will magically fit, and it will close timing at 480 megahertz. And no, it didn't. It so much didn't. I ended up thanking when it closed timing at 360, which was my next favorite frequency. So I started to analyze what were the problems. Of course, I have failed to do many basic things, which are usual suspects in this matter. I didn't do right the SLR crossings, which really is the big thing. If you don't get it right with a high-speed clock, you're just not going to get it. I didn't add enough piping between modules, so signals were taking too much to propagate from one to the other, so this was pulling the logic apart, and it wasn't able to close timing. I also didn't get right the high fan-out control signals, like reset, but also advanced crossings and some enables that I distribute around my logic. And, well, this last part, it's not so easy to detect, because when you go to see the list of violations, you may not see a violation in this particular signal. You may see a violation in the code that was supposed to run right, but that had to be stretched towards the point where this high fan-out signal is pulling it. So in these three issues, the story of my talk is I ended doing a lot of fine-grained placement. So these three first points, placement helped a lot identify them. Because once you put things in place, in the place that you think they need to be, then violation starts appearing in the paths that really are stressing the design. And then the final part, which is, so the first part, placement helped a lot, but I wouldn't say it was completely, it would have been completely impossible to do it without it. The last part is, I got the impression that Vivado doesn't really make, so I'm using Xilinx FPGAs for this project, didn't make a good enough job in placing the design. It's right now it's about 500,000 LUTs. And being a design with a lot of critical paths and where complexity is very high. So I got the impression that it was just rolling the dice too many times with random decisions. And when you do that in a small design, you get a high chance that it's going to get it right. When you do it over a 500,000 design, you're almost guaranteed to have a lot of violation, and it just can't process it. So the... Yes?
I'm wondering, with the implementation strategy, did you use a particular one Navarro Tobar? Did you use your own? Did you use them all? What was your strategy at that point?
I use them all. Yeah, it takes...
We do as well. So.
Yeah. I will show a screenshot with the 6 best of them that I tried at the end. But it's machine time is a lot cheaper than developer time. So, the way I got this impression is that violations don't appear consistently in the same paths. It's not the same module that is failing. It's not always the same register to register. It appears in one of the copies in my 7th chamber, and then you change a little thing, and then it appears in a different module in the 2nd chamber, but the other 7 chambers seems to be right in that particular module, so it's kind of inconsistent. So Vivado tells you that, the AMD documentation tells you that placement is going to help with this. It tells you to first try with hierarchical floor planning, and then if you if you just can't get it right, you just go to gate level planning. I haven't gone down that so far, but I'll tell you what I've been doing about hierarchical floor planning. So here on the blue part, it's a description of my algorithm. I don't want to go into. I just want to get the sense that it's kind of heterogeneous. It's not just one module that is replicated 32 times or something like that. It's got 2 sectors. Each one of those 2 sectors has some common infrastructure and then has 4 chambers. If one of those chambers has a lot of modules, some ones are used once, some others are used 3 times. Then each one of those is a big part of the code which has 1 matter and then 2 equal parts. So it's kind of hierarchical, nested, not very flat. I was intending for it to compile in this AMD Virtual UltraScale Plus 13P device. It has 4 SLRs. So the logical choice for me in the beginning was to just put 2 chambers per SLR, which is a second level depth in my hierarchy, and it failed. So I needed to go finer grained with the placement. But I asked myself, how deep will I end up needing to go in this placement? Will I need to go all the way down, all the way to the last entity? How would my constraints file look like in this situation? How will I go iterating over 6 levels of depth in inner structure? How maintainable would it be, this kind of script, when my algorithm evolves, because it's not fixed, it's not written in stone yet? And how easy is it to draft, in this case, a small constraints file for just compiling 1 entity and see how it goes? So I ended up seeing myself wishing to have a placement tool, which gave me this, which is user-friendly, so the backend does the heavy lifting. I don't have to look for the specific location of X, Y coordinates in the slices and in the ramps, which are different numbers from the slices and so on. So that it is aware of resources and utilization, so it automatically can resize P blocks if needed, and it reports the utilization on those P blocks while it's doing that. That it allows for 2 kinds of workflows. It allows for top-down workflow, which I call that to start with a coarse placement, maybe this thing I mentioned, that having just 2 chambers per SLR. And then if it doesn't work, I decide to go finer, and then I subdivide that P block into, I give it an inner structure, and then that inner structure is automatically propagated to everywhere my placement was in the beginning. So, and it also allows for a bottom-up approach, so I can go to just 1 entity, compile it, see exactly what shape of a P block it needs, what big of a P block it needs, and then go integrate it into the general design. And I wanted it to be reasonably easy to evolve, to maintain my placement, not that it is a pain to remake everything. When I change 1 little thing, I decide to give one of the inner modules more space or whatever. So, going into the description of what I did, I did a helper set of scripts in Python, which end up compiling the constraints file for Vivado. So everything starting from here is a work in progress. I haven't published anything yet. I intend to develop it a little bit more, and maybe if there is interest, I could open it, and maybe, well, we heard yesterday about open source licenses and projects and so on, so we could look into that. So this is what would be the definition of my fabric, of my FPGA. I've got 2 sections, the vertical one, the horizontal definition. In Xilinx devices, in AMD devices, the fabric is organized as columns, and then you've got 1 column which is all the way up to down of the fabric is the same kind of thing. These things being basically slices, RAM, and DSPs. And so I've got other things missing that are also in the fabric, which are modules, special modules like those ones I'm mentioning. I don't typically use it in my RTL, but they affect routability of the design if you want to make a P block that crosses these areas. So you'll notice there's not a uniform distribution of RAMs and DSPs. So every P block that uses those elements cannot be offset horizontally as freely as you want. It can be offset vertically, but not horizontally. And yeah, you can typically move slice-only P blocks, right or left, but it also depends on routability because of crossing these columns takes a little more time to route and so on. And then vertically, I just decided to go for the minimal vertical increment that has integer number of slices, DSPs, block RAMs, and ultra RAMs. So this is what it ended up doing. My coordinates are then in the X, the index in this longish stream of columns, and in vertical it's the number of vertical atoms in the device. So what's the user interface for this placement? I have two kinds of objects. I defined them in Python 6 syntax. I thought of doing it in kind of a YAML format or something like that, but you lose the ability to script the definition itself of the P block, which is interesting. You might want to do an iteration to generate this list of contents, for example, or something like that. So for the P blocks on the left, you define basically what are the boundaries. If you left one of these 4 numbers undefined, it automatically resizes for it. So what I typically do is when I'm doing bottom-up, I let it decide, then I try to compile, maybe change the shape, and then let it fixed. It accepts options that can be like, is the P block soft? So is Navarro allowed to move some logic out of it if it wants to? Does it have to contain routing? Oh yeah, I'm very slow. And then I define a list of resources that it uses and a list of paths that P block must use. And on the right, there's a box, which is simply a collection of other things, which are either other boxes or P blocks. And the thing is that it offsets them, it prefixes the paths in it, and prefixes the name of the P block in it. So you can iterate over it and create many copies of your thing. So this is an example of the usage. You run it, you get a screenshot that shows what columns are you using in the center, and then what columns you have in the neighborhood to the right and the neighborhood to the left. It tells you the shape of the slices, and also tells you the utilization for the P block, and if you're getting over it, like I'm getting over time right now. So, and then at the end, it outputs the constraints file. This is an example of the bottom-up approach. I just generate constraints and generate a wrapper for one entity and compile it. It closes timing. It seems nice. Then you hit to show me the routing, and you see the routing is completely going outside the P block. So this is a case in which when I put it into a bigger design, it didn't close timing because it didn't have this extra space available for routing, so that is something to take into account. And these are my results. So this is the same RTL on the left with no placement constraints at all for my P block, for my design, for the algorithm itself. Then a little inner structure with 8 P blocks, and the end, the current status, the current snapshot with this over 200 P blocks. As you can see, it's a lot more organized. It seems to occupy more area in the FPGA. Indeed, it occupies a little bit more because you're giving more room to each of one of the instances. Also, I was not very careful and I gave too much space to some blocks that didn't need so much. But at the end, I managed my thing, which is my goal, which is closing timing. To the left, I must say that these 2 columns have no placement or very little placement, but they benefit from the RTL optimization that I got by doing the placement. So at the end, even the 2 left ones are kind of taking advantage of this. And so 2 very quick slides. This is a problem that I've had a lot, and I ended up developing this. It's a methodology. It's not really just you get the idea and that's it. It's for serializing and deserializing data when you have a very structured record of information and you need to put it in the serial link, so you just needed to convert it to the vector. I ended up doing a lot of books in this because you need to concatenate all the fields, and then you need to slice and remember what exact indices you have. What I do is I make a combination record which has the object structure plus the standard logic vector, and I do one function that converts one into the other. And it's using a cursor that it's automatically increasing, so you don't have to keep track of what number, what indices each one of them is using, where each field is. And you can also use iteration in it, and you can also use call to this same function of a sub-record that has its own serialization, deserialization function. So at the end, you take this function and just define two functions that do it in one direction or the other, and it's quite convenient. And this other thing is, it's another solution to everyday problem. I ended up needing to know a lot of times in a faster clock what was the phase relationship to the parent clock. So I made a very small, it's like 50 lines or so, module that I have reused a lot. It's very light, so you just don't bother taking the outputs and putting them and then fanning out the output. You just put it wherever you need. And it basically takes the two clocks and has 4 outputs, which one is active when the phase relationship is a particular phase relationship. So you just take one of those 4 signals, or n signal, because obviously it's a generic, and then you know what's a phase relationship. You know you write the thing just in the bunch crossing that you need. And well, there's no need to maybe just time for questions.
Thank you very much, Alvaro. This is definitely a source for inspiration for many of us. Questions? Anybody?
Hello. You talked a lot how you fight the symptoms, but you haven't talked much about the causes. Meaning you have to understand your net list, like do you use a large memory that is spread over the entire chip? How wide is your data path? A switch matrix can route through something like 50 signals. So if I know I have a lot of signals, a wide data path coming from here and has to go in another direction, like a DDR4 memory channel is 512 or more wires. So have you ever looked into your net list and thought, how are things interconnected with each other? Yeah, and then you have all the other constraints with BRAM columns and so forth, which adds some kind of fragmentation in your design, because you will find your DSP blocks or memory columns or something only at discrete locations. And if you have to place a larger net list, you can actually over-constrain your system quite easily too. So have you ever looked into that one? And you haven't. And what was the key problem in the net list?
I think the approach is quite generalistic. My data path is basically like a huge pipe in which data is being processed and it's just handed over to the next module. And yes, there are intermediate points in which between modules you may have 1,000 lines or something like that. There are some modules that use intensive use of DSPs. There are some modules that make intensive use of RAM. It's not spanning over all the design. It's just at most, I would say 24 block RAMs is the most that a particular module uses. And the thing is, individually, all the things fit, and obviously there is enough room to pass like a few hundred or even 1,000 lines between the width of the two modules. So yes, those particular modules that are using RAM or DSPs, I put them in places where I know they can use them. The thing is, actually giving Vivado separation of each one of the blocks actually is proven to help. So I guess this is I really hit a problem that exists. Maybe you're right. Maybe I could have looked deeper into some of the parts, but yeah, I guess I didn't or not.
Yeah, it's somewhat related. Previously, when I've tried to do something like this myself, I found that, yes, I can make individual blocks very fast, but then the timing fails between the regions that I've blocked off. Have you had that, or is it just a facet of your design that it's, well, better coded than mine?
I had to improve the RTL a lot while I was doing displacement. When you compile just one unit and then require to have a line of flip-flops at the end to meet timing, then maybe that data is coming from unregistered RAM, and that's very slow. It closes timing when you're doing just one unit, but when you plan to move this data to some other module, it just doesn't close. So I had to add, while I was doing this, a lot of piping between modules.
Okay.
And also especially took me a lot of time was piping good enough these high fan-out signals, that control signals that go to all of the design. Because it's very easy to overlook how important they are, how they're going to pull from your logic to some place. So this placement helped a lot. It showed the violations in this path.
Okay, thanks.
Yeah, a short question. I would like to play with it. So I think it would be nice to, even in its current state where it's not completely finished, to have it published somewhere with a note that it's not finished. And maybe then also others can provide input to maybe make it better. So I would suggest to make it open source rather sooner than later.
Okay. Yeah, it takes a little time, as we saw yesterday, to do the due diligence and so on, but yeah, I definitely, if there's interest, yeah, we should do it. We should try to keep working at it on a more open format. Perfect. So write me after the conference to.
Perfect. Will.
Right, we're running a bit late. Maybe time for a last question. Anybody? All right, Francesco.
So first of all, a general comment about this. Like, this is we want to create a community. So the idea is that even if you don't share things properly, as we have learned that there is a way to do it properly, if we stay in touch with the forum that we are using, then you guys can stay in contact. So even if it's not officially released, you could start working at it together, which is a good thing. Then my question is on slide 13, where you had the table with several times. Yeah. So what's the different rows? What changes between one row and one row? And
it's different without implementation. I didn't. There was no room in the slide for the particular implementation. I can tell you, this one finally close timing was net delay high. It's performance explore net delay high.
Okay,
and,
so
and the other ones I don't remember exactly.
Changing the strategies.
No, it's the same 6 strategies. It's actually the 6 best for this implementation. I took them and I ran in the other 2. So it might happen that these 2 ones might have had another implementation that yielded better results. They're all performance implementations, so they're pretty good, but it might be that there was someone slightly better here and slightly better here. So I'm not completely sure that, but it was a lot of compile time and I didn't have time.
Maybe.
For this last design, it was 2 hours and a half in my machine.
Maybe a last comment at the risk of stating the obvious. Placement constraints are definitely the last resort. We need to make sure, just to follow up in one of the comments, to make sure that our net list is perfect, and then this is the only thing you can do to improve. Mm-hmm. But yeah, it's always good to look at the net list. Anyway, let's thank the speaker again. Thanks, Alvaro. And we move to the next one.